only does it make sure you understand your blood buffer system and how things are connected, but it makes sure you also retain knowledge on previous things we've talked about, like Le Chatelier's principle. Okay. All right, the last thing we're going to talk about is titrations. This feels a little redundant because you guys have actually already done a whole lab on this, but it is part of the acid-base chapter, so we're going to kind of briefly go through this. I'm going to introduce the idea of titrations with this slide right here. If we have an acid with a hydroxide ion, that is a neutralization reaction. This is an acid-base reaction. If you see on this top reaction listed, we have a strong acid, HCl, reacting with KOH, which is a strong base. You make water, and you have potassium and chloride in an aqueous solution. They'll be broken up and dissolved into their ions, but these are our products. Obviously, the strong acid and the strong base are neutralizing each other to make water. The second reaction, we have acetic acid, which is a weak acid. We know weak acids don't fully dissociate, and usually we write the dissociation reaction with a double arrow. But here, we're reacting it with a strong base. So notice we've only written a single arrow, okay? Why is that? Well, what this figure is trying to show is that it doesn't matter if you have a strong acid or a weak acid here. The fact that you have a strong base in both cases, it's going to force the reaction to make products. That base is going to hunt down every molecule of acetic acid in solution, and it's going to grab this acidic proton off of it. It kind of doesn't give it a choice. Acetic acid, if it was left up to itself, maybe only half of it, maybe 60% of it would disassociate. But when you put it with a strong base, that strong base is going to, like I said, it's going to find every molecule of acetic acid, take its acidic proton, and make products. So we don't write a double arrow on this equation. We have a forward single arrow in both. So what we're saying is that the reaction goes to completion. I think these points are kind of what I just said. The strength of the acid here is irrelevant. It doesn't matter because hydroxide is a very strong base and water is a very weak acid. Okay, we're forming water, which is a weak acid. Remember, our products are also acids and bases. But because it's a weak acid, we're not going to get a reverse reaction. These are called neutralization reactions because we have a neutral pH. We're just making water and a salt. Nothing on the product side is going to increase or decrease pH. All right, this is kind of what a titration is in a nutshell. I'm going to give you this scenario to introduce why titrations are useful. If we have a solution of acetic acid, okay, that's this one right here. We've used acetic acid a lot as an example of a weak acid. How can I find the concentration of acetic acid? If I have a solution of it, how can I find the concentration? Well, if we stick a pH meter in it, maybe we could find that the pH is 2.89, which is pretty acidic. That's a very low pH. And we can then we know that pH equals the negative log of H plus. So for given pH, we can just do 10 to the power of negative pH. Okay, we got rid of the negative on the side. The 10 undoes the log. So 10 raised to the negative pH equals concentration of H plus. We know those things. So we could get the concentration of H plus. But remember, acetic acid is a weak acid. Okay, if we have a weak acid, we get a double arrow here. There's our products. We get a double arrow. Just because we have a certain amount of product doesn't mean we have a certain amount of our weak acid. Okay? So just because we have a certain amount of H plus, we know the concentration of it right here, 0.0013 molar. It doesn't mean we know the concentration of acetic acid. Okay? But if we have that solution of acetic acid and we react it with a strong base, we are going to force every molecule of acetic acid here to react. So what that means is that the number of NaOH molecules needed, or the number of moles of NaOH needed to react with the amount of CH3COOH we have, the amount of acetic acid we have, we can determine the acetic acid concentration with that, okay? What I just said, if you didn't grasp that, is that the reaction will go to completion. We draw a single arrow here. If we know how much NaOH it takes to completely react with the acetic acid, then we can find the original acetic acid concentration, because we can use a mole ratio. If we know how many moles of NaOH it takes to react with X amount of acetic acid, we can do a mole ratio and figure out how many moles of acetic acid that is. Okay. So again, here's our acetic acid and NaOH reaction. Here's the steps of a titration that you guys walked through or saw with the lab we did the other week. In the flask, so I'll zoom in. We have a flask down here. In this flask, we have the acid and the pH indicator, which is usually phenolphthalein. And step number 2 is we're going to drip the base slowly in. The base is in the burette. The burette has markings. It measures milliliters in the burette, and we are going to drip it into the flask, drop by drop. And once we've done that, when the acid and the base have completely reacted, you will see that your solution remains pink. So when you've added a drop of NaOH and it turns the solution pink and it stays pink, then you know your titration is done. Again, we added more base and the solution went from neutral to slightly basic, meaning pink. That's because the indicator phenolphthalein changes colors based on pH. So the end result is this. The amount of base required to give us the amount of acid we started with. We know the amount of base that was required, that we used. We measured it in milliliters from the burette. And then you guys learned how to perform titration calculations. This is just saying, hey, this is what we're going to do. You've already done it. I'm going to work one titration problem. Likely I'll put a titration problem on the exam as well. So here's our titration problem. We titrate 5 milliliters of vinegar. In your lab, you did 10 milliliters of vinegar. Vinegar has acetic acid in it. And we titrate that 5 milliliters of vinegar with 0.1 molar NaOH. And it says 44.5 milliliters of 0.1 molar NaOH were required to reach completion. What was the original concentration of acetic acid in the vinegar? Okay, so anytime you're working a titration problem, number 1, start with the number of milliliters of base. Okay, so that's because we already know the concentration of the base. Or actually a better way to do it, because you know what, you could titrate an unknown concentration of base with a known concentration of acid. That's perfectly valid. So you start with the number of milliliters of the substance that has a known concentration. Here we know the concentration of base. It's 0.1 molar. And whichever number of milliliters corresponds to that substance, here it was 44.5 milliliters, start with that number of milliliters. So we're going to start with 44.5 milliliters of NaOH. And we want to ultimately get a concentration of acetic acid. Concentration is moles per liter, right? That's molarity, which is concentration. So we need to get moles of acetic acid. So if you remember from chapter 9, we had a diagram that we followed. Let me write that diagram out really quick. I'm going to zoom way in so that I write small. The diagram said this. We start with volume of substance A. We're going to convert to moles of substance A. Then we're going to convert to moles of substance B. Then you can go to, well, here we're not getting a volume. We're trying to figure out a concentration. So we're actually going to stop here. How do we do this? Step number 1 is you use a molarity of substance A. Step number 2 is a mole ratio. Now, what's going to happen inevitably, some people are going to look at a problem like this and they're going to try to use M1V1 equals M2V2. And I'm going to write in big, fat, blue letters, I'll write it down here, do not use M1V1 equals M2V2. Don't do it. It's not a dilution problem. It's a titration problem. Alright, so we're going to follow this diagram. So start with the volume of substance A, which is 44.5 milliliters. To use the molarity that's given to us in the problem, 0.1 molar, we need to be in liters. So we know there's 1,000 milliliters for every 1 liter. Now we can use the molarity. 0.1 molar NaOH equals 0.1 moles per 1 liter. So we have liters on, milliliters have canceled out. We have liters on top right now. We'll say for every 1 liter, there's 0.1 moles. That's step 1. We use the molarity to go from substance A in volume to moles of substance A. What's step 2? Let's use a mole ratio. Well, if we look at our balanced chemical reaction, for every 1 mole of NaOH, we need 1 mole of acetic acid. I'm going to write moles of NaOH on the bottom so they cancel. Now here's the deal. A lot of times people, when you have a 1-to-1 mole ratio, they want to skip this step. Because they're like, 1 divided by 1, that's not going to change my answer. But it does change your units. You're talking about moles of NaOH. Now you've converted to moles of the correct substance. Okay, so you're not going to get full credit if you don't use a mole ratio on a titration problem. Alright, so then we're going to have moles of acetic acid. So let's pause and get a number here. 44.5 divided by 1,000 times 0.1, you should get 0.00445 moles of acetic acid. Please always label what substance you're talking about. Acetic acid here. Now to get molarity, we said it's moles divided by liters. We have moles on top already. Why don't we just divide it by liters? Well, what is our liters of acetic acid? The problem tells us we have 5 milliliters of vinegar. Well, we need to know, and that's our acetic acid. We need to know that volume, but in milliliters, or sorry, liters. So I'm going to take 5 milliliters, convert it to liters. Okay, there's our volume in liters. So we'll just divide by that. So we'll do 0.00445 divided by 0.005. And I got a molarity of 0.89 molar. Okay. So that's an example of how to work a titration problem. That concludes our Chapter 10 material. So if you guys have questions on this, please write those questions down, email me, or jump in a Google Live